attempt to say something useful. We begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. Again, I thank you for these students and just pray that you'd help us use this time wisely, Lord, just to accomplish what we need to today, Lord. In your name I pray. Amen. Let me get this out of my system right quick. Theorem 5 is this theorem for products. It is, let H and K be subsets, subgroups of G. Number 1 says if H or K is normal in G, then the product HK is a subgroup of G. And number 2, if they're both normal, then the product is normal. So, and the reason I'm spending time in here is because I think the proofs are useful and it's healthy to see them worked out, but it's simply the case we don't have enough time in regular class to do everything. So sometimes stuff overflows to here. 1, if, without loss of generality, suppose that K is the normal subgroup of G, right? Then if we have HK is an HK, right? Then notice that we have HK equals to HK H inverse H, because I just multiplied by the identity here, right? But then look harder. What we got? What is this? This is conjugation by H of an element in K, right? So this is in K, right? So this is equal to like K2H, which of course is an element of KH. Here, let's say that this thing is going to be K2, which is an element of H by the fact that we're given that K is a normal subgroup of G. So what's that say? That implies that HK, that was supposed to be capital H. I think I saw why you guys were, I now see why you guys are like, what? Because I need capital H there. So HK is a subset of KH.
Wait, is K2 in H or is K2 in K?
Oh, K, good gracious. Goodness. Great. Googly moogly, what's wrong with me? Okay. Then what? And then similarly, and I won't go through the details there, but similarly, you can show that KH is a subset of HK, and that implies, of course, that we have HK is equal to KH, and remember by lemma 2, which we did last time, what do we get for lemma 2? If KH is equal to HK, it implies that they're both subgroups. Number 2, if we have H and K both normal in G, then HK is a subgroup of G by 1, right? I mean, 1 says if either is normal, then the product is a subgroup. So it remains to show that the product is normal, right? So let G be an element of G, and HK an element of HK. We're still working with the notation that little h means H is in H and little k means K is in K. So notice then that G, golly, look at that, I'm still doing this. You know, I've got this like, I'm supposed to put the G on the right inverse on the right side, right? These stupid notes I have written, put G inverse on the left side. Goodness gracious, God, yeah, so annoying. But anyway, you guys can tell me what to do. And you can also see why it is you need normality of both H and K here. How do I, because I know that H and K both conjugate back to themselves again, that's normality.
Can you multiply by G inverse and inside?
Yes, exactly. And I'm going to take that and make it a G inverse G, but your heart was in the right place. Because then, you see what we have we've got conjugation of an H element, we've got conjugation of K element. So this, of course, is equal to H1, K1 for appropriate choices, which is, again, an element of HK. G was arbitrary, right? So this shows that G, HK, G inverse is a subset of HK, which by the normality test implies that HK is a normal subgroup of G. So there's that. Theorem 6 we talked about yesterday. Corollary 1. I just want to take like a breath to talk about why is it true. G is a finite group, H and K are subgroups. We already know Theorem 6. Does it make sense? I mean, the thing was, in Theorem 6, we defined this bijection, right? What was the bijection? It was sigma of H comma K equals to HK, right? And the point is, we can argue, like here's why it's an injection. How about this? So we've got H1, K1. Oh, well, I did that in class already. Let me not belabor that. So we proved that it was an injection. In fact, it's onto. Can you show it's onto? Why is sigma onto? What's a typical point in HK? Okay. Then apparently sigma of HK equals to HK. So, yep. Okay, so it's surjection. The book is not wrong to say it's obvious. It is here. Okay, but the larger point from the proof of Theorem 6 is that sigma is a bijection, right? Which means you can use it to count. And let's see here. And so I think that's all that this comes from, basically, is that, you know, how many things are in there in H cross K? This has what? This has H times K things in it, right? Take the Cartesian product of 3 things with the Cartesian product of 4 things, you get 12 things in the 2 tuples. That's counting. And so if that's isomorphic to HK, then of course, you know, if this is isomorphic to HK, then we get this counting, right? I mean, but you don't even need the normality there. The normality is needed. Sigma is a bijection even when it's not a homomorphism is the thing. We needed the normality to get the homomorphism. The normality came from the fact that we could commute elements. We could commute elements. Even if we can't commute the elements, we still can get that sigma is a bijection. It's just not a homomorphism. We can still count with it for corollary 1. Corollary 1 is actually from the proof of Theorem 6, to be careful. Corollary 2, we have a finite group, H and K normal, intersections 1, the product of the orders of H and K are G. So how do you prove this corollary 2? Let's see here. We have everything we have in corollary 1, right?
So we know that the order of G is also equal to the order of HK.
The order of G is less than or equal to the order of H times the order of K. Is that right? Why do you say less than or equal to? Do you say?
I didn't say that.
Oh,
I said it's
equal to.
the order, and I said like HK, like in 1. Right?
Oh, okay. So I'm sorry.
So I just like.
I'm an idiot. So the
So I said the order of G equal to the order of HK, like together.
oh, HK together. I'm sorry. Yes.
Yeah.
That was corollary 1. I've already forgot. Oh, yeah. Duh. But then what? Oh, but this is equal to this, right? What is that?
That's where we drew that conclusion.
Oh, I'm sorry. How do I get the isomorphism? Oh, here's the comment. So HK is a subgroup of G, right? Because G is, and but we also have that. Oh, that's it, right? So this is a sub. I mean, that's it. I'm sorry, I'm an idiot. We already have that H. How do we know HK is a subgroup? Because of like Theorem 5, right? In fact, it's a normal subgroup, in fact, given the conditions of corollary 2, right? HK is a normal subgroup of G. By the counting you already pointed out, the order of G is the order of HK. So if you have a finite group and you have a subgroup of the same order, so that implies that HK is equal to G. Right? And then we know that HK is isomorphic to H cross K by corollary 1. Hence, G equals to HK is isomorphic to H cross K.
Is that back to 6?
There was Theorem 6?
Yeah.
Oh, I'm sorry, Theorem 6, yeah. All right. Try not to spend too long in here on this and keep it moving. This example actually is worth going through, though. So here we have the GCD of M and N being 1, and I want to have G equal to, say, generated by A. So G is cyclic with the order of G being Mn, right? In other words, the order of A is Mn, right? So we can construct subgroups. Let H be generated by A to the M. Let K be generated by A to the N. Right? Because these are relatively prime, you can argue that well, I mean, you know, AM to the N is equal to what? It's equal to A to the Mn, which is equal to 1, and down here, A to the N to the M is A to the Nm, which is 1, right? So it must be what? So the order of A to the M must divide what? The order of the group, right? One of those. On the other hand, the order of A to the N must divide what? Yeah, Mn. But these are relatively, I'm not sure I'm getting to the point very fast, guys. I'm sorry. Huh. Well, let me not belabor this. There's something stupid I'm missing here. So you can argue, because of the relative primeness, you can argue that the order of H is N, and there's a gap in my logic. I'm sorry, guys. It may not be a big gap. It's that time in the day. You know how I am. The order of H is going to be N. The order of K, rather, is going to be M. Admittedly, there's a gap there. I should explain why. And I don't think it's hard to explain why. I just don't see it at the moment. Can you guys tell me why?
Because if the order of the group is Mn, then obviously the order of the cyclic, right? That's so we know the order of H is less than or equal to Mn, right?
Right.
And the same for K.
Right.
And we already showed that a to the mn equals 1, so that's the order of h's n. Because a to the m to the n is 1. If that's true, then the
Well,
order...
So the
well, I mean, this shows that the order of h is less than or equal to m, right? No, sorry, n. More to the point, the order of, sorry, order of a to the m. My question is, why does it have to equal n?
they're relatively long.
Can you elaborate on that?
Trying to think through it.
Since they're relatively prime, there's the theorem that says the subgroup is unique to the order of
I'm having trouble here. So let's suppose that am to the j, right, is equal to 1 for some j less than n. We should come to some contradiction, right? And/or we should acknowledge that there's some obvious thing we're not using. So am to the j is equal to 1, right? Which means that mj has to divide mn. What does that mean?
So
So mj equals mn times...
I mean, if m and n are relatively prime, right?
right.
And, oh, I don't know. I'm sorry, you were saying, fine.
So mn equals kmj.
All right.
So then
N equals
kj,
Oh, okay.
which is contradiction.
N equals to kj, right?
Which means j is greater than...
but k is in the integers because it divides it.
Yeah,
That's
so
like,
either k is greater than or equal to 1. But if it's greater than, we have a contradiction, so k equals 1. So
This implies k is,
but
N equals
we
k.
can't.
K.
J can't be equal to n. Yeah, it's a contradiction.
It's a contradiction.
because this
Yes.
Yeah.
and this contradiction. All right. I'm working with very low brain power right now. I'm trying to warn you. So I get hung up on the smallest of things.
They don't really like to show it in the book that much either.
Well, but I mean, on the one hand, it's okay to assert by common sense it's true. On the other hand, we should be able to give an account of why it's true if asked.
Yeah.
That's the thing. So anyway, yes, so we have ruled out the case less than n, and there is doubtless at this point in the course a theorem we could be applying to avoid this explicit minutia. So anyway, getting to the point here, the order of h is equal to n, the order of k is equal to m, right? What's the intersection? H intersect k, what's it got in it? It's just got 1 in it, right? Because m and n are relatively prime. Yeah. So this just has 1 in it. And so look, we have all of the ingredients we need. Are h and k normal? There are a billion subgroups of an abelian group, so yeah, they're normal, right? A subgroup in an abelian group is normal. So we've got everything we need to use corollary 2. And what's that tell us?
G, well, single group A is isomorphic to
It's, yeah, h cross k, right? And these, of course, are isomorphic to what?
HK.
Right, but true, it is
Oh,
hk,
okay.
true, but not what I was trying to get at.
A to the M, A to the N.
Right. Well, that's just equality, but more to the point, what is am? And I mean, h is what we call Cn, right? And h it's the cyclic group of order, excuse me, k is the cyclic group of order m, so that's Cm, right? Or if you don't like these for your token, this is not equality because these are not the standard presentations of Cn. I mean, Cn is this thing. Let me use B.
All the way to BBN
Yeah. And you see that's not really this, right? A to the m, a to the 2m. I mean, I'm being picky here, but I would say they're not the same point set. They're isomorphic, yeah. Just like we could just as well say Zn, Zm for A. There's another one we could do. Or we could pick on nth roots of unities, lots of choices. I'll save the rest for tomorrow. So, you guys got homework questions? Example 8 is example 8 is much like this, except it gives us, this is very, very nice because, we had before, in your homework before, we had what? Given h and k with the greatest common divisor of the order of h and the order of k equals to 1, right? Then you proved that h cross k is cyclic, right? Order mn. Well, it is cyclic. That was your homework problem you proved before. This is different. This is saying, given a cyclic group made from relatively prime product orders, right, then it is isomorphic to the Cartesian product of those suborders, cyclic groups. So this is it's the opposite direction, and it allows me to do things like say, I don't know, pick your favorite two relatively prime numbers. What do you want? 7 times what? 7 times 13. Oh, making me. That's what you're. 7 times 13. That's what you were going to say. All right.
3 and 5.
3 and 5. Oh, okay. Well, that seems. That's boring. So this is Z3 cross Z5. I mean, this is so stupidly useful if you're trying to find which finite abelian groups are isomorphic. It's a major tool. The other major tool is given by example 8, which I'll talk about tomorrow, which talks about, order p squared, what happens there. So I'm going to shut up about that. You guys have homework questions? Go for them. I think you do. I mean, if you don't, I'll just finish my lecture, but trying to behave. Believe it or not.
Oh yeah, let's do that one.
Normal subgroups in Dn would probably be helpful for addition problem that asks about normal subgroups.
What are the normal subgroups in Dn is your question.
I don't know if that's what the question is. Do you have in parentheses? So I'm guessing it's somewhat.
It's 2.8 number 17.
2.8, number 17. This is not an admission. This is a training.
Correct. Yes.
Yeah.
All right.
It admittedly might help.
So we've got Dn, as usual. And we're supposed to show that every subgroup of the subgroup generated by the rotation, A, is normal in Dn. And if n is odd, we're supposed to show that if it's a normal subgroup, it's either the whole shebang or it has to be a subset of A. How are A and B different? I'm sorry, I'm missing something here. Can you guys explain to me the difference between A and B?
A and B, they're just the different elements. It's like the X and Y.
Part A the question, part B the question.
Yeah.
Oh, never mind.
One is showing that every subgroup of Dn, I think that can be generated by.
No, so it's saying you're looking at the cyclic group A.
Yeah.
Any subgroup of that is normal in Dn.
Yeah.
B is n is odd, and we're given that K is a subgroup of Dn.
Oh, a normal subgroup of Dn. Oh, I got it now. So part A says prove that any subgroup of the rotation group is normal. Part B says prove. That's it? That's the only normal.
Yeah. prove that
So, oh, if it's odd.
If it's odd, then it's the only.
Okay. Now I'm on board. So various methods exist, of course, to do these kinds of problems. I think I'm going to try to direct calculation route since I don't have much brain power today, and it seems like a possible way to do it. With the subject to the usual terms and conditions, right? The order of A is n, the order of B is 2, and ABA. ABA equal B. Okay, so this is the dihedral group, order n. And we're supposed to let K be a subgroup of the subgroup generated by A, right? So it's a subgroup of a cyclic group, right? K is a subgroup of a cyclic group. Therefore, what? What can we say about the subgroup of a cyclic group? It's cyclic, right? So that means that K must be generated by A to the power, say, J, for some J, right? Since it's a subgroup of cyclic group, cyclic. Now, what else can we do? So then what do we do? We can let G be an element of Dn, right? What's an arbitrary element of Dn look like? How about this? G is B to the, what do you want? Pick a letter, any letter. Just not A, B. Oh, X, I like it. B to the X, A to the Y, right? For X and Y and Z, right? Of course, you could be less generous, but certainly that covers it. I mean, we could take X between 0 and 1, and we could take Y ranging in the numbers from 0 to n minus 1. That would suffice, but certainly this also covers all our bases. So if I look at G, let's see here. I'm trying to think what's the right way to proceed here. I got a lot of different things going in my mind. I'm going to try to do, let's let, run out of letters here, Z be an element of G, K, G inverse, right? My goal is to show that Z is an element of K. If I can do that, that shows that K is normal, right, since G is arbitrary. So what does this Z look like? G, what would K look like? Elements in K are A to the J to the what? To the whatever. To the whatever, right? What's the whatever there? Q. Okay. Sure, why not? Take it, Q, and then G inverse. So what's G? G is B to the X, A to the Y, A to the JQ, right? And then G inverse is what? It's b to the x, a to the y inverse. And here's how it goes. The b's will annihilate in a flash of light eventually. B to the x, a to the y, a to the jq. This, of course, is a to the minus y, b to the minus x. Let's make our life easier here. This is b to the x, a to the jq, right? But then we can, let's see here. So at this point, I find it convenient to break into cases. Or I could develop a lemma, which I don't have yet. I'm going to break into cases. Case number 1, b to the x equals to 1, right? Thus, z equals to a to the jq, which is an element of k. Good. Otherwise, x is equal to 1, right? Well, otherwise, b to the x is equal to b, right? Thus, z equals to b, a to the, good grief, I can't write at this level, b, a to the jq, b to the, well, b, right? And then the rule is, I mean, you can, since I wrote that, b, a to the minus jq. This is how the dihedral group works. There's a lemma that I proved, or we should prove at some point, which says that b, a to the j is equal to a to the minus jb. You can prove that.
Doesn't it just follow from ABA?
Indeed it does, yeah. And induction, yeah. And so if BB is otherwise, known as, there you go, a to the minus jq, which of course is an element of k again. So in other words, z, however you slice it, z is an element of k, which then implies, of course, that G inverse is a subset of k, which tells me that k is normal in Dn. Does that make sense? What?
Never mind.
Oh, okay.
I was just going to say, 'cause we started with z equals g, k, g inverse, and we ended up, when we, in the second case, we had b, a, j to the cube, b is equal to z, right? Could we then just say, obviously, b is equal to g is equal to its inverse in that case? Or? We started with z is g times a to the jq g inverse. And then in our second case, where bx, b to the x, b, we have z equals b, a to the jq, b. That might not be fair to it.
But I don't think we know that that's in k yet. We have to prove that's in k. So it's important to commute the b to make it go away. Anyway, we still have part B to do, so what do you guys think about that? Part B was what? If n is odd, so that k is either, if k is odd and it's normal subgroup of Dn, then either k is equal to Dn or k is a subgroup of the cyclic group generated by A, right? In other words, the ones we found in part A are all that there are defined except for the whole thing. N is odd. Now, if n is even, what happens? So we're trying to say we have K, a subgroup, a normal subgroup of Dn, n odd, right? Implies that either K is a subgroup of the cyclic subgroup generated by A, or K is equal to Dn. So I think the way to prove something like this is to do what? Assume K is normal, right? And so we should assume, easy, assume n odd, right? Assume K normal, right? And suppose that K is a subgroup of Dn with K not a subgroup of A, right? Then our goal is to show that this K is what? Right. The question is, how are we going to do that? What does it mean for K not to be a subgroup? So K is a subgroup of Dn, but it's not a subgroup of An. What does that mean? So it means that B A to the J is an element of K, right? For some J. How does that help us? If K is going to be normal, what else do we know? We know that G inverse K, oh my goodness gracious, that is impossible for a thing. It's hardwired in my brain that the G inverse goes first. Look, I just cannot stop. GKG inverse is going to be a subset of K, right? It's in fact it's equal to K. It has to be equal to K if K is a normal subgroup. That's for all G, right? All G and Dn. Can you pick? So my question is, what we want to do, right, is we want to pick what can we pick on to conjugate this BA to the J element by G to make something kind of perverse happen? What if we conjugate by B? What happens then? B inverse is B, right? Yeah. So we get A to the J, B, right? Thank you. BA to the minus J, right? Now that has to be an element of K, right? So thus, if BA to the J in K implies that BA to the minus J is in K, right? So that means where there's 1, there's 2, right? Unless, if n were even, we could have the situation like let's see here. How does it go? Like n equals 4, a2 is equal to a to the minus 2, right? A squared is its own inverse. Can you guys think of anything else? But we just scratched the surface here. We can conjugate with everything and see where it takes us, right? This should be able to allow it. By continuing this process, hopefully we can force k to be dn, is the thought process here, right? What else can we conjugate by? Oh, I'm not sure that, what's that? Actually, I say that, but now that I think about it, I'm not sure that it's actually that helpful. I mean, if I conjugate by a to the k, or let's say a to the x, right? Does that even help? I don't think it even helps, does it? Because if you look at this, right? It's no help. See, because that's b, a to the minus x, a to the j, a to the minus x, right? Oh, it is helpful. This is what? J minus 2x, yeah. So that has to be an element of what? K, yeah. And what can we can let x be what? I mean, anything, right? So it can be 1, it can be 2. Yeah, so this implies that k has, it's got b, a to the minus j, but what else does it have? Of course, it's got b, a to the j. What else is it? It's got b, a to the j minus 2, right? It's got ba to the 2 minus j. It's got ba to the j minus 3. It's got ba to the 3 minus j. Once you know this is in there, you know that the negative's in there by conjugation by b.
Why did you get the 3 though? Because it's 2x. So like.
Oh, thank you. Very good. So that should be 4. Hey. Thank you. 4. You're right. Et cetera, right? So. I'm trying to visualize it. I'm trying to visualize how to explain this. I mean, so. I'm trying to think, why is it that we have the whole last half of the dihedral group because of that? I guess pick whatever J is, right? I don't know how to explain that. God. I mean, I could pick a specific n and try to explain the argument. There's got to be a better way to kind of organize that thought. There's this kind of pairing, right? Whatever you pick in there. Let's see here. Suppose sometimes just working a specific n will be helpful. So maybe let's just talk about 7. 1a squared, a cubed. Why did I pick 7? b to the 4th, a to the 5th, a to the 6th, a to the 7th. ba squared, ba cubed, ba to the 4th, BA to the 7th, good grief, 5th, BA to the 6th. Why did I put 7 there? What's wrong with me? It goes to A to the 6th, right? We've got a 1 over here. So here's D7 for you. Suppose, just for the sake of argument, that we picked 3. Suppose that was our BA to the J that we picked in our K, right? Then what's the minus, what's BA to the minus J? Where is that? Right, so this is conjugated, sigma B, so to speak, takes us to there, conjugation by B. And then BA to the J minus 2 is over here, right? That's this one, which by conjugation gives me, then 2 minus 6 is paired to that one, right? And then, let's see here. Minus 4, where's that go? That's the 5. 5, you say? That should be 6, so that also goes there. There's no help. What about?
But then 4 minus J would give you 1.
This one?
Yeah, the 4 minus J gives you 1.
So that's just the same cycle as the one above it.
Oh, I was
Just
thinking,
A6.
yeah, okay, I got you.
J minus 6.
How do I get to the 2 and the 5? Somehow I get there. Right, if I take, let's see, if I take B, A to the 4th, and I conjugate by A, right? What's that give me? So, there it is. So this goes to there under the sigma A map. Which then by conjugation by B takes me over to here, right? And that's everything. Oh, but I still got to get to, anyway, I'm pretty sure that conjugation by A moves me what? Like that, right? I think I see the way to argue now. We should think about conjugation, and we should view them maybe graphically. So the conjugation by A moves us 2 to the right, left like that, right? And what is, so yeah, conjugation by A moves us 2 to the left, and then conjugation by B, it includes the, it brings us, goes the other end. And so wherever you start, because n is odd, these motions will cover all of this part of the dihedral group, right? Then the question, of course, is, well, where does these come from? Well, you can multiply these to get any of those, right? It's a group still. So like BA times B gives me A, Once you have A, you got everything else. And you see why this breaks down if n is even. Because if we're even, then these conjugation maps, they don't have to like loop back on everything. They can, it's the oddness, which is the devil's in the details here, but it's the oddness. And maybe we can just we can prove that more explicitly. What's a maybe D4? You guys can tell me what's a normal subgroup of D4, which is maybe not just a one a squared. What do you say? BA squared. Well, how'd you know that already? Oh, okay. Cool. Is that a subgroup? B is its own inverse. A squared is its own inverse. And B times A squared is the product of the two things in there. And it's its own inverse. So that, and that's a normal subgroup, which that would require some calculation, but that's a normal subgroup, which is not a subgroup of, this is not subgroup of A right here. I mean, it's got four things in it, and they're not just one A. It's just clear it's not a subgroup. Neat problem. I think you really get to learn a lot about, oh man, I'm in trouble. I gotta go. Class over. We were not here at this time.